Good day and welcome to our today's class on simple stresses and strain. We are of course at numerical number 10. The question says the figure below shows a steel bar. Of course, this is our steel bar of cross-sectional area 250 millimeter square. Now it is held firmly by the end support and it is loaded by an axial force of 25 kilonewton. We are asked to determine the reactions at L and M, the extension of the left portions also, and we're given E, which is our modulus of elasticity, to be 200 times 10 to the power of 9 Newton per meter square. Now, first thing, we are going to determine our reactions at L and M. Number one, we are asked to what? Determine reactions at what? At L and M. First thing I'm going to be doing is I'm going to be bringing out the free body diagrams of this steel bar. So for section LM, let this diagram here represent section LM. Of course, I'm having RL, which is tensile, RL, which is tensile. I'm having a length of 0.25 meter. Of course, now from here, if you consider this bar to be in equilibrium, of course, we know that the forces to the left-hand side must be equal to the forces to the right-hand side. That is, their summation must be equal. So what I'm saying is this: we are having RL to the left. If I add it with RM also to the left, it must be equal to, of course, the summation of all the forces to the right. But we are having just 25 to the right, so it's equal to 25 kilonewton. So from here, if I call this equation 1, I can make RL the subject. RL will be equal to what? 25 minus Rn. Also from equation 1, I can make Rm the subject. Rm will be equal to 25 minus RL. So this is what I have. So now, to get the tensile force of section LN to the right, what am I going to be doing? I'm going to be minusing this compressive force that is coming in, which is RM. So I'm having here to be what? 25 minus RM. And of course, to show that this section here is of course at equilibrium, we are having RL to the left. We are having what? 25 minus RM, which is equals to RL. So this is what we have. So next, I'm going to be drawing the free body diagram, of course, of section NM. What I have N, I have M, I have our length to be 0.6 meters. What I have. Next, you can see that we have RM from the diagram. RM as a compressive force coming in from the right. Now, what do we have next? In order to get the compressive force that is coming in, to know the real compressive force that is coming into this section NM from the left, what do we have? We will take away this force here, which is RL. So here I'm going to be having 25 minus RL in order to get the total compressive force that is coming into this section. So of course, I'll be having 25 minus RL. And of course, 25 minus RL, of course, equals to RM. That is, we are having RM coming here, RM coming here, which are the same. It means this body also is also at equilibrium. We can call this section 1, and of course, this section 2. So next, if you look at this body very well, you will note that we have support at the both ends, which is fixed. And also, for this, you have to note that the body above, the body is supported, or we can say the bar is fixed at both ends. Now, if this bar is fixed at both ends, it implies that there will be no change in length. It implies that if there is no change in length, what it means is that the extension produced here will be equal to the compression produced here. That is, this section here will be equal to this section here, although this section is in tension and this is in compression. Now it means that the extension of the first section will be equal to the extension of the second section. Now of course we know that from our formula of extension or elongation, the L of course equals to PL all over EA. If I express this in terms of this first section and this second section, what am I going to have? I'm going to be clearing this side. I'm going to be the L1 will be equal to what? Will be equal to P. Now for the magnitude of pull for the first section, of course we said is RL. I just wiped the diagram off, but the magnitude of pull for first section is RL multiplied by its length, which is 0.25, all over what? All over E. Now we are having E to be what? It was given from the question to be 200 times 10 to the power of 9 multiplied by our area, which is what? 250 millimeters square. Now if you look here, we are using all our units in meter. We are not working with millimeter. So we are going to be converting millimeter square, of course, to meter square by what? By dividing by 1000. By dividing by, sorry, 1 million, because we are having squared here. So 250 divided by 1 million, of course, can be written as what? 250 times 10 to the power of minus 6. So this is what we have for our first elongation. That is for the first section. Now for the second section, which is this, I'm having my magnitude of pull. I just wiped the diagram off, but my magnitude of pull is Rm. Of course, this is it here. We are having Rm here, which is the same thing as what? 25 minus RL. Next, what do I have? Multiply by the length, which is 0.6. All over what? All over the modulus of elasticity, 10 to the power of 9, multiplied by what? 250, which is the area, 10 to the power of minus 6. So this is what I have. Now, what am I going to be doing next? I'm going to be equating these two. Of course, we have already said they are equal, so I'm just going to be equating them. I have RL multiplied by 0. What? I'm going to have RL multiplied by 0.100 times 10 to the power of 9 multiplied by 250 times 10 to the power of minus 6. This is equal to Rm times 0.6 all over what? All over 200 times 10 to the power of 9 multiplied by what? Multiplied by 250 area times 10 to the power of minus 6. 10 to the power of minus 6. Now, this is what we have. Next, we'll be multiplying both sides of this equation by, of course, 200 times 10 to the power of 9 multiplied by 250 times 10 to the power of minus. If you do that, of course, we know that this and this will go. We will be left with what? RL multiplied by 0.25 will be equal to Rm multiplied by 0.6. Very simple, just multiply both sides by the denominator. You're going to have what I just have here. So now what do you see? Of course, from here we can divide both sides by 0.25. Divide both sides by 0.25 implies that RL will be equal to Rm multiplied by 0.6 all over 0.25. Now, coming down here, don't forget that Rm is equal to 25 minus RL. Rm is equal to 25 minus RL. If I put that here, what am I going to have? I'm going to have RL to be equal to what? To be equal to 25 minus RL multiplied by what? Multiplied by 0.6 all over what? 0.25. Now, if you solve this, what are you going to have? All you just have to do is open this bracket and what? Divide both sides by the coefficient of what? Of RL. You get your value of RL. So if you do that, RL will equal to 17.647. RL equals to 17.647. So this will be your value for RL. Now, if you come here, in order to get the value for Rm, that is the reaction at M, what will you do? You can just impute your value, that is the value of RL in this equation here. So it implies that this equation says Rm equal to 25 minus RL. So we have gotten our value for RL. nothing but 17.6647 is our value for Rn. Rm will be nothing but what? 7.353 kilonewton. That's 7.353 kilo. So this is our reaction at L, and this is our reaction at M. Of course, we have solved the first question we are asked here. Secondly, they said we should find the extensions of the left portion. We should find the extension of the left portion. We're going to be wiping this side. Extension of the left portion. Extension of the left portion. Body diagram earlier of the left section. The free body diagram of the left section, I drew it earlier to be something like this. I have my Ln. Here I have RL, and I said that what? I said that this other part is what? 25 minus Rm. This is 0.25. Okay, so this is what we have. This is, of course, the free body diagram of section Ln. I drew it earlier, but I just drew it again in order for us to make reference with it. Now, to get the extension of the left portion, of course, we can name this one, which we have done previously. To get the extension of this portion, that is the L1, what do we do? How do we get the extension of this left portion? Of course, we know that extension L, the L is nothing but what? P L all over what? All over A. This is what we have. But for here, of course, our magnitude is of course RL, and of course we know that RL is the same thing as 25 minus RM. So our magnitude here will be RL. We have our length, which is 0.25. We have our area, which was given to us as 250 millimeters square. We also have our modulus of elasticity as 200 times 10 to the power of 9. So we are just going to be substituting our values, and we'll be getting the value of the L1 in no time. If I wipe this side, what I'm going to be doing, I'm going to be substituting my values. Of course, here is going to be 1, here is going to be 1, here is going to be 1. Because the modulus of elasticity is common for the whole bar. So change in length of the first section, or we can say the elongation of the first section, will be equal to the magnitude of pull, which is RL, multiplied by the length. Of course, we are giving the length to be 0.25, that is of the first section, all over the area, which is 250 millimeters square. Converting to meter will be nothing but 250 times 10 to the power of minus 6. Multiplying the modulus of elasticity, which is 200 times 10 to the power of 9. So my RL is nothing but, of course, we have calculated RL area on to be 17.647. It will be nothing but 17.647 multiplied by 0.25 all over 250 10 to the power of minus 6 times 200 times 10 to the power of 9. So L1, that is of the first section. Now, if you multiply the numerator, multiply the denominator and divide them, you have your elongation or your extension of this portion, which is the left portion, will be equal to nothing but 0.0000882 meter. So L1 will be equal to 0.0000882. So this is our extension of the left portion. I hope you understand and you comprehend all what we have just done. You can leave your questions if you have any in the comment description box, and also your contributions if you have any too. Be sure to like and subscribe to our channels. Hit the notification button to get more and more of these numericals as we'll be uploading them subsequently. Thank you for watching.